We are now going to discuss an interesting topic in trigonometry. And this actually goes back to something you first learned about in algebra class, and that is complex numbers. Let's just take a very quick minute to remember what complex numbers are. Back in algebra, you learned that you cannot take the square root of a negative number. This is not a real number. However, what we did back in algebra was we decided to split this up. So minus 9 is the same thing as square root of -1 times square root of 9. Now square root of 9 is 3. And then what we did, we came up with this I, which stands for the imaginary unit, where I equals the square root of -1. And because of this, then we came up with complex numbers. Now, if you recall, complex numbers have two parts. So here's an example of a complex number. 4 plus 3i. 4, if you remember, was called the real part. And the 3i was called the imaginary part. So here's what we're going to do in this trig class with these complex numbers. First of all, we like to call, in trig class, we're going to call complex numbers z. So let me just rewrite this complex number, call it z. And what we're going to do, we're going to graph this imaginary, or this complex number, on what we will call a complex plane. And it's actually pretty simple, because what they decided to do is, if you have a complex number, you take the real part and you graph that like it's the variable x, and then you take the imaginary part of your complex number and you graph it like it's y. So it's almost like, in a minute you're going to see, we're going to graph this complex number 4 plus 3i. When we go graph it, it's like 4 is x and 3 is y. Matter of fact, I'll do it quickly. So I'm not going to label this vertical axis y. Instead, for now, I'll just label it as the imaginary axis and this as the real axis. But really, you can still think of it as the x and y axis. So 4 plus 3i, 4 on the real axis and 3 on the imaginary axis. So this point here represents 4 plus 3i. We can call it z. Let's say that I wanted to graph an imaginary number -2 minus 3i. There's -2 plus 3i. I'll just do one more for fun. How about -1 -2i? All right. not too difficult, right? Just the real part, it's like your x variable, the imaginary part's like your y variable. Now, I will not tell you what the ultimate purpose of doing all this is, because I'll just let it unfold as I show you, but there is a reason why we're doing all this, because down the road it makes certain kinds of calculations much simpler. I'll just leave it at that. So here's what we're going to do. So what we've done so far is, I'll just go and call it like this. So when we graph complex number, we call this the rectangular form, because you can think of x and y as like the rectangular coordinates. Since we just concluded talking about polar coordinates, let me graph a point and remind you about rectangular and polar coordinates and how to go back and forth. So let me go and still label this as the real and imaginary axis. So let's just graph the complex number 3 plus 3i. So 3 on the real axis, 3i on the imaginary axis. So this right here, this point is 3 plus 3i. And we would say this is the rectangular coordinate of that point. Now what if we wanted to go ahead and take this point, and instead of naming it 3 plus 3i, what if we want to rename it as a polar coordinate? Now you remember, polar coordinate says the distance to that point would be r, and the angle would be theta. And if you recall, we went back and forth between rectangular and polar coordinates. Two of the little formulas we came up with is that x in rectangular coordinates is r times cosine theta, and y r times sine theta. And also, if we're given a rectangular coordinate, the way we calculated r was the square root of x squared plus y squared. And when we needed to find the angle, one of the ways we could use was the inverse tangent of y over x. All right, this is our review of what we did with polar coordinates. So here's what we're going to do. I'm going to now take and write a complex number in rectangular coordinates with x and y. Except now I want to rewrite this complex number, and instead of having rectangular coordinates, I wanted to put it in polar form, which means I'm going to go ahead and replace the x with r cosine theta and replace the y with r sine theta. So I'm getting rid of the x and the y and replacing it with r's and thetas. So I'll label this as rewriting. I'll still call it z, but instead of x, I put r times cosine of theta, and y, I'll put r times the sine of theta. Of course, I still got the I here. Now what they like to do here is, we have two terms here, so you have r in both. Here's the form that we like to write it in. I'll factor out the r, and I'm going to move I in front of the sine. So this is called the polar form of a complex number. So in a minute, I'm going to do a problem where I'm going to take an imaginary number in rectangular coordinates, the normal way we have imaginary numbers, but I'm going to rewrite it into the polar form of a complex number. So let's just do that. Think of a fairly simple example. How about one plus I? So 1 is the real part, I is the imaginary part. I'm not going to graph this right now. If I did, it would just be like 1 on the x-axis and 1 on the y-axis. I want to go ahead and rewrite this in polar coordinates. So this is rectangular coordinates, and it's like how would I write this in polar coordinates? So it's just like what we did going back and forth between rectangular and polar coordinates when we first learned about polar coordinates. 1 is like my x. This is like my y. Of course, if you want to, you can think of a 1 being there. So x is 1, y is 1. Since I know x and y, what I need to do, I'm going to use these two equations. Use this equation to find r. Use this equation to find theta. So r, x is 1 squared, y, the imaginary part, is 1, so I square it. 1 plus 1 looks like r is square root of 2. Theta is inverse tangent of 1 over 1, which is inverse tangent of 1. Now you go to your unit circle. Now this is an inverse tangent, so you say, what's the angle where the tangent is 1? Which is the same thing as saying, what's the angle where the sine and the cosine are the same? And in radians, that's pi over 4. And if I were to graph this point, then yes, that would make sense that the angle, I mean, just if you're not sure if this is the real coordinate and the imaginary, here is 1 plus I. So what we're saying now is this distance is square root of 2, and this distance is pi over 4, which is also like 45 degrees. So it all makes sense. So now, this is the form we write it in though. We write z equals r. R is square root of 2. Cosine of theta, which is pi over 4, plus I times sine of theta. Now, it might seem a little strange at first because you're saying to yourself, well, I know what cosine of pi over 4 is. That's a special, I got square root of 2 over 2. And I know what sine of pi over 4 is square root of 202. And if you plug those in, then this ends up turning into the rectangular coordinate system. So for now, we're going to leave it in this form where we have the r and the theta. So this is now the polar form of the complex number 1 plus I. Now, there's one more additional part to this, and this gets a little goofy in terms of we're going to use a formula that even in the book it says it's very complicated to derive the formula. So we're just going to give it to you and then show you how to use it. There's a very famous mathematician named Euler, and he came up with this, and they named it after him, Euler's formula. It's interesting. So let's take a quick look at this. Look at the form of this polar coordinate, r times cosine theta plus sine theta. Look at this Euler's formula. What he discovered was that cosine theta plus I sine theta. In other words, if you look at this polar coordinate form, this is the stuff inside these parentheses. That's the same thing that's here. He discovered that this is equal to e to the I theta. E is the natural exponential number. If you recall back in algebra, this is like the natural exponent. E equals like around 2.6. It's just one of these special numbers in math. So Euler discovered this. Now if you look, let me write over here, a few minutes ago, we came up with the polar version of a complex number, and it was r times cosine of theta plus I times sine of theta. Actually, let me just write it here. I should have just written it here. This is what we came up with a few minutes ago. The polar coordinate version of a complex number. What we can do now is we can take and plug that in for this, which really means we can replace this whole thing with e to the I theta. So we give this a name. This is called the exponential form of a complex number. So sometimes in this class, we've had to go back and forth between two different kinds of things. We did it with angles, radians and degrees. We've been doing it with points on a graph, rectangular coordinates and polar coordinates. Well, now we're going to do the same thing with complex numbers, except there's actually going to be 3 types of complex numbers. So let me just summarize them here, and then in the next video we'll actually start working out some problems. So to express complex numbers, we can first do it in a rectangular form. Z equals x plus yi. Then we learned about how to write a complex number in the polar form, where z equals r times cosine theta plus I times sine of theta. And the key is here, I won't rewrite them, but going back and forth between rectangular and polar, you have to use these equations. And now a third way to write a complex number is the exponential form. And that's going to be z equals r e to the I theta. So here's what's going to happen. They'll give you a complex number at rectangular form. Matter of fact, I'm going to do the one I've already done. This was the first problem we did. So that's rectangular form. We've already done this problem and converted it into a polar form. And the polar form, if you remember if I have was this right here, we found out that r was square root of 2, theta was pi over 4. So if we write this in the polar form, it was square root of 2 times cosine of pi over 4 plus I times the sine of pi over 4. And now, so this is the polar form, but there's a third way. Now going from the polar form to the exponential form is very simple, because the exponential form, you notice, in the polar form, you have r and theta. We have the same thing in the exponential form, r and theta. So it's a matter of just copying down these numbers. So the exponential form, you write r e to the I theta. So when you do some problems, they're going to give you a complex number and rectangular coordinates. Now to convert that to polar, you basically have to figure out r and theta, and you have to do some math and use those formulas and equations. But then once you write it in polar form, then they're going to ask you to write it in exponential form, but it's very simple, because once you have the r and theta, you just write it into the exponential form. All right, in the next video, we will do some problems like this.